So two more types of points of concurrency. If we have medians, so that word median means middle, so it connects a vertex of a triangle with the midpoint of the opposite side. So you pick a vertex, and if you go to the midpoint of the opposite side, that would be a median. You can get that from any vertex. So just like it's circumcenter and incenter, we can do all three medians in a triangle, and we're going to do it again with all three types of triangles. Yeah, let's use blue. So vertex, if I go to the midpoint of the opposite side, I have a median. So if I pick the midpoint of this side and connect the vertex, connect the vertex to that midpoint, and then connect this vertex to this midpoint. And again, they will all, if they're done all precisely and everything, they will always connect and be concurrent. Okay, so notice that one is inside. Again, this one, they're always going to be inside because we're never going outside the triangle. We're checking median. So if that's the middle, it's kind of close. My other one was really crooked. And it's hard to write straight on here. So if you connect medians, they are concurrent. We're going to call this the centroid. Always inside. And I'm pretty sure that one's off. Pretty sure that one's way off. Okay. Back and my pen back. So if I have a vertex to the middle, vertex to the middle, and vertex to the middle, and that is called your centroid. Okay, so the centroid has a couple it has a property. The medians intersect at the centroid. It is 2/3 of the distance from the vertex to that midpoint of the opposite side. Okay, so what's that look like? You're going to see, depending on what your picture looks like. Here's a picture. Whoa. There we go. This looks super crazy and scary. Come back here. That's my whole toolbar. Let's go. Pens. And I need some colors. Why did the colors go away? Okay. So, that looks really scary there if you're looking at it from that, all those little equations. But here's the basic idea of this. If you divided each of these things into 3 parts, it would be a 1:2 ratio. Okay, the one that connects to the vertex is twice as long as the other. So this is 1/3 of the whole thing. This is 2/3 of the whole thing. So that's where this stuff is coming. The pieces are half and double of each other. The pieces are half and double. So if you're told you have a centroid, okay, so like this one here, P is the centroid. So YV is 12. Now YV is a whole thing. Okay, that's a whole median. So if we divide that by 3, so we need the thirds, 1/3 is 4. So the short piece would be 4, and then the longer piece is twice that, or 8. So YP is actually 8, and PB is actually 4. So it just separates it into that 1/3, 2/3 relationship. If you know the whole thing, divide it by 3, and then that gives you the short piece, and double it for the long piece. Here's 3 examples using the same diagram. I'll just reuse it. So if CG is 4, well, CG is what? That's the longer piece. So if this is 4, the shorter piece would have to be half of that, or 2. GE is 2. So when you're talking about the two pieces, it's half and double. When you're talking about the whole thing, it's 1/3, 2/3. Okay? So for part B, that information goes away and we start over. If DG is 7, okay, that's the short piece. If the short piece is 7, the long piece is twice that, or 14. Okay, so the pieces are half and double. The whole thing is divided 1/3, 2/3. And so here, if AF is 18, that's the whole thing. Okay, this is the whole thing. So divide it into thirds. 1/3 is 6. So the short piece is 6, and the longer piece is double that, or 7. So GF is, 12 is 6, and G is 12. Okay, it just gives it that 1/3, 2/3 relationship. And there is one more. If we could do the altitudes. The altitudes go from a vertex, starts at a vertex and is perpendicular to the other side. So the altitude would be like that. Okay. Now remember, you might remember when you did area of triangles someday, sometimes we had to do it outside of the triangle. The only way we can do this one perpendicular is if we extend that side. That would actually be an altitude of that triangle. Now the altitudes are concurrent as well. I go vertex perpendicular, and then this one ends up being here, and that point of concurrency is called the orthocenter. Okay, it's called the orthocenter. If I go in a right triangle, this is perpendicular to the opposite side. This is perpendicular to the opposite side. The orthocenter is actually right there. It is the vertex. That's the orthocenter there. And then in an obtuse triangle, it actually ends up being outside the triangle. We have to draw it. I have to extend them because otherwise they're not going to fit like this one. I have to extend it so that I can be perpendicular to it. Anyway, I'm just going to do the piece right there first. This one I have to extend so I can be perpendicular to it. And they don't meet. But if we extend these guys, they actually meet out here. So this is another one where in an acute triangle it's inside. In a right triangle it's on the triangle. Obtuse it's outside. Now one thing about the orthocenter, there really is no special feature to it. Our circumcenter was equidistant from the vertices. Our incenter was equidistant from the sides. The centroid gave us that 1/3, 2/3 thing. The orthocenter doesn't really give us anything special, it just is there. Now at the end of this file here, and I will make sure you have access to that as well, is this. I made this nice little chart, but that kind of sums all 4 of those things up, points of concurrency. And I've always let students have access. I don't expect you to memorize which one is which. You can look at this chart to do that. So notice in this one here, I got the red ones, and that's the the ones that are the same. Oops, sorry, got things popping up. Okay, those are your other centers.